Good afternoon. I'm Edo Berger, faculty co-director of the science program at the Harvard Radcliffe Institute and professor of astronomy in the Harvard Faculty of Arts and Sciences. It gives me great pleasure in both capacities to welcome you today to our annual Next in Science Symposium. This year, focusing on the James Webb Space Telescope and its impact on our growing understanding of the universe and on public interest in science. This is a hybrid program, so it's great to see so many people here in the audience, especially with the weather we've been having, and to welcome those joining us virtually from all over the world. We're also only 4 days away from the great North American eclipse, so this is an exciting time for the public's participation in astronomy more broadly. The James Webb Space Telescope, or JWST, is the most ambitious, complex, and expensive telescope ever built. It was launched into space on December 25th, 2021. And I still remember watching the launch in the early morning hours with my then 3- and 5-year-old kids, jumping and screaming in excitement while they were trying to open presents. Even now, watching the folded JWST separating from its launch vehicle and beginning its long journey gives me goosebumps. So let's take a moment to just recall that from 2021.
Séparation Webb Space Telescope. Go Webb!
We do have confirmation of observatory separation. The James Webb Space Telescope, amidst applause here in the Mission Control Center, now taking its first steps in pursuit of cosmological discovery. And there is the view from the upper stage camera on the Ariane 5 looking at the James Webb Space Telescope as it moves gently away from its launch vehicle.
Okay. Amazing, right? The story of JWST begins much earlier than its launch in December 2021. Already in the mid-1990s, following the successful repair of the Hubble Space Telescope, NASA formed the HST and Beyond Committee to plan for future space telescopes. The committee recommended a large infrared space telescope in its 1996 report, and a short while later, the 2000 Astronomy Decadal Survey recommended the so-called Next Generation Space Telescope as the highest priority for the field in the 2000s. The concept was an 8-meter telescope, later descoped to a 6.5-meter, to be launched in 2010 to an orbit in L2, the Sun-Earth second Lagrange point, located roughly 1 million miles away from Earth, and with a price tag of about $850 million. It was quickly realized that reality was a bit more complex than that, and in 2005, the launch was delayed to 2013, and the price tag rose to $4.5 billion. In 2010, the launch was again delayed to between 2015 and 2018, and in 2011, the House of Representatives threatened to cancel JWST due to cost overruns. It was thanks to community advocacy and intervention from some senators that this decision was reversed, and it led to the project moving on with a price tag of $8 billion. This was not without controversy. In a 2010 Nature article talking about JWST, it was described as the telescope that ate astronomy. In 2018, the launch was delayed again to 2021 after the sun shield, which we'll see in a second, ripped during practice deployment. So at least some folks found some humor in the situation, but also optimism, given that the delays were at least at a rate of less than 1 year per year. The final cost of JWST is about $9.7 billion, of which $8.8 billion went to constructing the telescope and launching it, and the remaining $900 million are for mission operations and to support the science. The mission lifetime originally was set at a minimum of 5 years, but is now anticipated to be 20 and perhaps even longer years, which is fantastic. So why infrared, why space, and why such a complex telescope? So let's see. This is what JWST looks like, and for scale, you can see all those people standing next to a mock model of the telescope. So JWST's key goal is to observe the universe in infrared light, light at wavelengths of about 1 to 30 microns, which is not visible to the human eye. Observations in infrared light are key for studying the most distant galaxies in the universe, whose light is redshifted by the expansion of the universe, regions of galaxies obscured by dust, such as the birth sites of stars, and cool objects, such as the formation sites of exoplanets, of stars, of exoplanets and the exoplanets themselves. And here I mean temperature cool, although these objects are also cool. We will hear about some of these topics from today's speakers, as JWST is completely revolutionizing these wide-ranging areas of investigation. At the same time, JWST has produced stunning images of the cosmos that have been splashed all over the news, not to mention that the very first image from JWST was released by none other than President Joe Biden. This is a testament to the impact and unique role of astronomy in general, and JWST in particular, on public interest in science, a topic that we'll also touch on today. Now, since infrared light is mostly blocked by the Earth's atmosphere, it must be observed from space. This is why the telescope needs to be up there. And equally important, since warm objects emit infrared light, JWST has to be kept extremely cold, less than 50 degrees Kelvin, or about minus 370 degrees Fahrenheit. Otherwise, its own infrared glow will completely blind its view of the universe. So this is the reason for placing JWST in an orbit nearly 1 million miles away from Earth, and for its enormous sun shield, about the size of a tennis court. And this sun shield is quite amazing. It's made from 5 layers of material called captain, with each layer being the thickness of a human hair. And that leads to an astonishing 550 degree Fahrenheit temperature differential between the side that's facing the sun and the telescope itself. Now, because of its enormous 6.5 meter diameter gold-coated beryllium mirror, about 6 times the area of Hubble's mirror, and about 60 times the area of its predecessor, the Spitzer Space Telescope, and because of its enormous sun shield, JWST had to be launched folded up, which we saw in the original movie, and then unfold origami-like in space. Its large mirror produces incredibly more sensitive and higher resolution infrared images than ever before. So here is a comparison of an image of the same region of the sky from the Spitzer Space Telescope, the predecessor of JWST. It's a 0.85 meter diameter mirror as opposed to JWST's 6.5 meter diameter. And you can see the difference in sharpness as well as in the sensitivity of the telescope. Here's another example comparing a beautiful image of this region called the Pillars of Creation from the Hubble Space Telescope. So this is quite a sharp image taken from space. And here's what it looks like with James Webb. So you can see, even compared to the Hubble Space Telescope, the images are incredibly sharper, and because of the use of infrared light, they can also penetrate through this dusty region and reveal all of its details in a way that's never been possible before. Now, JWST carries several instruments on board with quirky names such as NIRCam and NIRSpec and MIRI and NIRIS. These instruments are designed to collect detailed images and spectra, and we will see results from them today. Okay, with that introduction to JWST, I'm particularly excited about today's event because the Next in Science series provides an opportunity for early career scientists whose creative, cross-disciplinary, and cutting-edge research is thematically linked to introduce their work. And as you will see, our 4 speakers today bring a lot of energy and creative thinking to make excellent use of JWST and to assess its role in the public's interest in science. Indeed, with the new capabilities of JWST, it is critically the work of early career scientists that's really leading the field. And our speakers today are responsible for some of the more than over 600 scientific publications that have already been published from JWST in just its first 2 years of operations. Before I introduce today's speakers, I would like to give you a quick orientation to the program. The program will have 2 sessions with 2 speakers each, separated by a 10-minute break. The sessions are organized to take you on a journey from the nearby universe to its distant edge and then back home again. After the individual presentations, we will have a group discussion and audience Q&A, which will conclude at 4:40 p.m. Audience members, whether you're here in person or online, are welcome to submit questions at any time during the program using the Slido link provided on the screen behind me and posted in the chat of the Zoom webinar. We will try to get to as many of these questions as we can during the Q&A. Before I introduce the first two speakers, I want to take a moment to acknowledge the members of the Radcliffe Institute Leadership Society and our annual donors who are watching this afternoon. Your generosity keeps Radcliffe programming free and open to the public, and we thank you. We also want to gratefully acknowledge the Melanie Mason Niemiec 71 Current Use Fund for Science, which is supporting this event. I'm also grateful to my fellow science co-director, Professor Immaculata De Vivo, the Radcliffe Institute staff, especially the Academic Ventures and Engagement team led by Becky Wasserman, and the events team led by Jessica Vickland, and to Radcliffe Fellow and Fellow Astronomer, Dr. Andrew Baker, for helping with the Q&A. And now to the speakers of the first session. Our first speaker of this session is Dr. Sierra Grant, a postdoctoral researcher at the Max Planck Institute for Extraterrestrial Physics in Germany. Dr. Grant will tell us about building new worlds, witnessing star and planet formation with JWST. Our second speaker of the session is Dr. Caroline Morley, assistant professor at the University of Texas at Austin. Dr. Morley will tell us about a glimpse into alien worlds, the first 1.5 years of studying exoplanet atmospheres with JWST. It's now my pleasure to invite Dr. Grant to the podium.
Okay, good afternoon, everyone, and thank you all for being here. It's great to see so many people in person attending what I think is going to be a really lovely afternoon of science. So I really want to thank the organizers for setting up this day and for inviting me to participate. So today I'm going to be talking about how JWST is changing our understanding of how stars and planets form. So in the galaxy, in space, in galaxies like our own and in others, there are clouds of gas and dust. And these clouds are called molecular clouds. And they can look fluffy and translucent, like you see here. They can be highly structured, like in the pillars of creation, like Edo already showed. And they can be these vast vistas, like we see here in the Carina Nebula. And in these clouds of gas and dust, when the conditions are right, when the gas is cold and dense, gravity can start to take over and start to form stars. And so when this happens, at the initial stages, there's some movement to the cloud. And that movement, as that gas collapses down, you will start to form a star at the center. The star will rotate with that angular momentum of the cloud. And that also forms a disk of gas and dust around these young stars. And this is where planet formation takes place. And so here I'm showing an image of a protostar. So in this image, you can see better here, in the very center of this image is our very young, still-forming star. And this star is blocked out. You can see this dark lane of material here. That's the disk. That's the disk of gas and dust around this young, still-forming star. And JWST is producing these beautiful images of the earliest stages of star formation, like we see here. But if you want to understand planet formation, we don't get such beautiful images from JWST because we're looking at the very, very center of this image. And at that scales, we're not getting these beautiful pictures, but we are witnessing, in some ways, the formation of planets. So if you want to understand the planets that are forming in these new disks of gas and dust around these young stars, you have to really zoom into this region. And so that's what I'm illustrating here, where we have our protoplanetary disk, this disk of gas and dust around this young star. Our disk is accreting material from the disk onto the star via the star's magnetic field lines. And with time, the system will evolve. All of these small dust grains that start out very, very small, smaller than the width of a human hair, those dust grains will collide and they will grow and they will start to form the cores of planets and then the planets themselves. And so with time, the system will evolve until the disk material is cleared and you're left with a planetary system, something that looks maybe like our own solar system, where you have a star at the center, our mature star now, surrounded by a planetary system. And if you want to understand this outcome, this planetary system outcome, you have to understand what's happening at the beginning stages. So everything that's happening at the protoplanetary disk stage will impact the composition of these planets, the masses of these planets, and what this system architecture will look like in the end. So we really want to understand these first stages of planet formation. And so here's just this illustration, and just to orient you, these disks go from the star disk connection here out to 100 AU or even larger, where 1 AU is the distance between the Earth and the Sun. So these are big systems, maybe not big compared to what we'll hear about later in the afternoon, but this is pretty large. And in these systems, these disks span a wide range of temperatures, from very, very hot in the inner disk to very cold in the outer disk, in particular in the cold, shielded middle of these disks. And that allows molecules to exist in different states, in different regions in the disk. So here I'm illustrating the water snow line. This is the region that delineates where water can exist as ice versus where it can't. So beyond this line here, the disk is very cold, and our water is condensed out onto dust grains, and it forms these icy mantles, these icy coatings to our small dust. Within this snow line, the disk is too hot for that ice to survive, and you would get the sublimation of these ices into the gas phase. So you'd have water vapor in these inner regions. And it turns out that most planets, we think, will form within the inner 10 AU relative to their host stars. And this is exactly the region that JWST is most sensitive to. So with JWST, although we're not getting, in most cases, very beautiful pictures, we're still probing this exact region where these planets are forming. And the main way that we do this, and the main thing that I'll talk about today, is how JWST is observing the gas in these inner regions, these inner planet-forming regions of these disks. So here I'm showing this GIF of a water molecule that is bending and stretching and rotating. And we have many, many, many of these molecules, and JWST is observing this movement of these molecules. And so this movement creates a photon that is emitted at a certain wavelength. And different molecules, as they move differently, will emit different spectral lines. And so this is the forest of spectral lines that you get from all of your water molecules in your disk. And so this is what JWST's mid-infrared spectrograph, MIRI, would see for water, for instance. So this is a model of water, and this is the molecular fingerprint of how we would identify water in an observation from JWST. But we can not only identify that water is here, we can also tell the properties of the water, because this spectrum will look different if the gas is very hot versus if the gas is very cold. So if we see these lines in the data, we can not only tell that water is present, but we can also tell the properties of the water that is there. But it's not just water. I'll just highlight a couple more molecules that we get just in this wavelength range covered by MIRI. We get CO, which is one of the most abundant molecules in space. We get C2H2 and HCN, which we think are important for prebiotic life. We have CO2, which is observed in planetary and exoplanetary atmospheres. We think this is a way to try to link them to their formation. And we have OH, which is an important molecule for many chemical reactions. It's also a product when water is destroyed, so we can then balance water with OH to see how water is evolving in a system. And so in this way, JWST allows us to study the composition and the conditions and the evolution of these disks as they're forming planets. So we can visualize, we can see the material that is going into these planets as they form. So now on to the results. But before I do that, I just want to acknowledge that I only have 20 minutes, and I could spend 2 hours talking about all of what we've learned just in the first 2 years. So I'm just going to put this up. I don't expect you to read this, but I want to highlight how much work has been done. When this talk, when the recording is posted online, I encourage you to go back to this slide and look at some of these papers, because there's a lot of amazing science from incredible scientists that I can't get to today. So please use this as a resource. Most of the results that I will talk about today are coming from the MIRI Mid-Infrared Disk Survey team, or the MINDS team. This is a program that I'm a part of. It's a guaranteed time program led by Thomas Henning at the Max Planck Institute for Astronomy in Heidelberg, Germany. This is our team that I'm showing here. It has many incredible scientists, including many early career researchers. So these are students and postdocs who are doing really incredible work and really driving the science in the team. So I showed this image before, and I really want to focus on this inset here. This wavelength region is really packed in molecular emission. And so that was the focus of the first paper on disks with JWST. So I'm showing the data here in black for a disk orbiting a star called GW Loop. And GW Loop has this bright CO2 feature, which you can see here. So the data is shown in black compared to this model in red. And this model is made up of all of these molecular species that I've shown down here. And with Spitzer, JWST's predecessor, we could only identify that CO2 was present. It was the brightest thing there, we could see that it was there, but we couldn't identify anything else in this spectrum. But now, with the incredible data quality that we get from JWST, we can see that this is pretty packed full of emission from different molecules. And we even make the first disk detection of 13 CO2, which is just highlighting how much carbon dioxide is in this system. But it turns out that the water is fairly weak in this system relative to others. And so a potential explanation for that is that we have a cavity in the inner disk around this star. If we have this inner cavity, then maybe this is formed by planet. It's possible. It's not the only explanation. But if we have this cavity, recent work from a graduate student in the Netherlands, Marissa Vlasblom, has shown that you can carve out some of this hot water that would exist in this system. And if you do that, you can deplete the water that you would see in your JWST spectrum while leaving the other molecules fairly bright. So we'll have to follow up on this source to be sure, but that is one possibility. So I keep saying that planets form in protoplanetary disks. We know this is true, but it's actually surprisingly hard to find these planets as they're forming. And currently, there's only one system where unambiguously we detect not just one, but 2 planets in the act of forming. And that system is PDS-70. So this is an image from the ALMA Observatory down in Chile. And what we see here is there's PDS-70, the star, at the very center of this image, not visible. This is a star that's slightly less massive than the sun, but fairly comparable. Around PDS-70 is an inner disk of gas and dust, very small. We have this big cavity here, and then we have this outer ring of gas and dust. And in this cavity exist 2 protoplanets, PDS-70b and PDS-70c. These planets are more massive and farther out than Jupiter and Saturn in our own solar system, but in many ways, they're somewhat analogous to each other. And with JWST, we're able to zoom in to really study the inner regions here, this inner disk around the star. So if this system is analogous to our own solar system, if we have Jupiter and Saturn out there, then in the inner regions is where we would be forming something like Earth, Mars, and Venus. And with JWST, we can study this inner region. And what we found in this paper published by Giulia Parati last year was that there's water in this inner disk around this star. So we're seeing for the first time water in this disk where we know that two planets are forming in action. So water is obviously very important for our own Earth. Maybe we were wishing that there was less of it today. But this is really exciting to be witnessing planet formation in action and to see ingredients necessary for life present in those systems. But JWST is also telling us other things about water. It's telling us about how water is delivered to this planet-forming region of these disks. So I'm coming back to this illustration of our protoplanetary disk with our snow line. And as our dust grains are orbiting around their star, they experience drag because of the gas in these disks. And that causes these dust grains to drift inwards with time. And so if these dust grains are drifting inwards, eventually they're going to be crossing their water snow line. And that will take all of this ice in the outer disk and release it into water vapor in the inner disk. So if this happens, we can get an enrichment of water in this terrestrial planet-forming zone. If we stop that from happening, for instance, if we have a giant planet that is locking up material in the outer disk, then we can have an inner disk that is relatively dry, is relatively devoid of this water. And this may be something that's similar to what's happening to PDS-70. I just showed you that there's water there, but it's a pretty small amount compared to many other sources. So maybe these giant planets in PDS-70 are holding back this icy material and leaving the inner disk relatively dry. So if we see small disks, like on the top, where the dust disks are very small, that may mean that we'll have more water emission in the inner regions. And that's what was found by Andrea Bonzatti et al. Last year, along with his collaborators, which is part of the JDisks collaboration, which is a US-based collaboration of JWST disk studies. So here is a plot from the press release where this is showing a sample of water lines in the Miri spectra. In purple is one of these small disks where we think lots of drift has happened, compared to one of these large disks shown in white, where we think that this material is not making it into the inner disk. And what Andrea Bonzatti found is that not only did these small disks show more water, they specifically showed more cold water. So we're seeing water just as it's crossing that water snow line. We're witnessing water just as it's being liberated off of these dust grains. And so we can then tell about how these disks are evolving with time and how the chemistry is evolving with time. And I just want to note that this work is being expanded upon with more sources and additional analysis by a graduate student here at Harvard. So that is work to be on the lookout for in the near future. So everything that I've talked about so far, all of these results, are mostly for disks around sun-like stars. This is totally fair. We want to understand how our own solar system likely formed. But how representative are stars like our sun in the universe? Well, it turns out if you take a sample of 100 stars in the local neighborhood, which is representative of the galaxy as a whole, of those 100, 6 will be white dwarfs near the end of their lifetimes. Okay. 20 will be stars that are similar in mass to our sun. There'll be a couple that are much larger, twice as massive, and there will be a couple that are around half the mass of our sun. And then 74 of those 100 will be what we call M dwarfs. And these are the smallest stars that exist. And here I'm showing the mass range of M dwarfs, and in fact, below this limit, these objects can no longer fuse hydrogen in their cores, and so then they're not considered stars. And this would be then a brown dwarf. And that's something that Caroline will talk about next. But these stars are super, super numerous. They're the most abundant stars in our neighborhood and in our galaxy. But not only that, but these stars also host the most terrestrial Earth-sized planets. So here I'm showing the number of these close-in Earth-sized planets, where close-in is within 50 days, a 50-day orbit of their star, and Earth-size is between the size of Earth and the size of Neptune. I'm showing this as a function of the mass of the starlet they orbit. And this is just an illustration here. It's based on the work of many, many people. It's very hard to get these numbers. But just as an illustration, massive stars do not host these planets. These planets do not really exist around massive stars. And even when you get to stars like the sun, only 50% of sun-like stars are going to host these Earth-sized close-in planets. So if you want to study these planets, which we do, you have to go to very small stars, because on average, these small stars host one Earth-sized planet, close in, likely in the habitable zone, potentially. And so if you look back at this, all of these little red points, on average, are going to have at least one of these planets. And so this is a huge number. This is a huge population space for studying Earth-sized planets. But what do we know about their disks and about how these planets form? It turns out that we know surprisingly little, because they're very, very faint. And so you need really big telescopes, really powerful telescopes to study them. So here I'm showing a Miri spectrum of a disk around a sun-like star. It's pretty typical of a disk around a sun-like star. And these are the first two disks that we looked at, two of the first, around very small stars. And if you are like I was in August of 2022, you are asking, what are these bumps and what are these wiggles? What are these features? Why does this look so different than anything that we had seen before? And it turns out the answer is that this is carbon, carbon, and more carbon. And in fact, we've detected 7 new hydrocarbons in disks for the first time, and we've detected them in really high abundances. So I just want to go through this spectrum of this disk around a low-mass star. This is submitted for publication by a graduate student in the Netherlands, Aditya Arabhavi. And what Aditya has found is that this spectrum is full of hydrocarbon chains, these big molecules that we wouldn't necessarily expect to be there, including things like this benzene ring that we see here. And in fact, we're not even reproducing all of the emission. So there's stuff here that we can't even identify yet. So this is a really different chemistry in these small stars, in the disks around these small stars, than anything that we had seen before. We thought probably they would be different than sun-like stars, but this is really different. And we don't really know why, because this is kind of a shock. This was a surprise, a happy surprise. And so I think with more observations from JWST, and this is something that I'm working on in the next few years, and with complementary observations from other telescopes, we'll be able to solve this mystery of why there's so much carbon in these systems. So I'll just say that the discoveries that we've made so far only make us more excited for the discoveries still to come, because the discovery space is really open. And then I just want to finish by acknowledging that none of this would have been possible without all of the thousands of people who have been working on JWST for years. So we are sitting in the shade of the tree that these people planted. So they had a dream and they made it happen, and we get to reap the benefits, especially as here we are early career scientists who are speaking today. So we really owe a great debt to them. I'm very grateful for that. It's a privilege, and it's a privilege to tell you all about it today. So thank you.
And it's now my pleasure to welcome Caroline Morley to the podium.
Okay, hi everybody, it's great to be here. I'm really excited to tell you about how JWST is totally revolutionizing our field of exoplanet atmospheres in just the last couple years that we've been getting data from this telescope. But let's rewind and talk a little bit about exoplanets. So we'll jump in here. So this is a picture of the whole sky, and we're going to see where the exoplanets appear starting in 1991. Okay, so I'll play it and I'll talk at the same time. It plays a ding whenever an exoplanet is discovered. So the first exoplanets were discovered by looking for that pull from the planet that pulled the star back and forth. Oh, it's loud. I'm going to make it a tiny bit quieter. There we go. That pulled the star back and forth, and you could look for that gravitational tug. Then we started looking for planets that actually crossed in front of their host star, and we would see a little tiny dip in light that we called a transit. We started making dedicated missions that this was their only job, to look for these little dips of light to find planets. And so the Kepler Space Telescope is one of those. And you can see the Kepler field because it just looked at one field in the sky just above the plane of the galaxy. And you can see we know of thousands of planets all appearing right there. And then we launched another mission, TESS, that looked all over the whole sky. It's still up, it's still looking. And so we're really filling in the whole sky. And so it's an amazing accomplishment. We now know of over 5,500 planets as of 2024 outside of our solar system. And so the resounding truth now, after all of this science, is that when you look up at the night sky, that star that you're looking at very likely has a planet that's orbiting it. We might not have detected that planet yet, but there's likely a planet there. But, and this is pretty amazing, that planet may look very different from any of the planets in our own solar system. Okay, so we're going to show a plot that looks like this. This is going to show you the year, the length of a year on the planet, the orbital period on the x-axis, and the mass of the planet on the y-axis. Let's pop up the solar system to give us a little bit of context here. So here's the solar system, right? Jupiter, Saturn, Uranus, and Neptune are gas giants in the outer solar system. Earth, Venus, Mars all fall on the plot. Mercury and Pluto, I put Pluto on the plot, are just below our plot. Now let's plot up the exoplanets. Here they are. They fill in everywhere. So when people first found some of these close-in planets, these hot Jupiter-sized planets really close to their star, whipping around the star every 3 days, they didn't even believe that they were real, but they are. They're really there. And so we just see all of these different kinds of planets. And now we're really moving from just being able to detect the planets, which is so exciting, but being able to see what these planets are actually like and characterize what we can see of those planets, which is their atmospheres. So how do we do that? So we use a special technique when we're lucky enough to have a planet cross in front of the star, transit in front of the star. And so when that planet is in front of the starlight has to go through the planet's atmosphere to reach us. So if there's no atmosphere there at all, you would always see exactly the same transit depth. But if you have an atmosphere there, and there's something in the atmosphere that absorbs at a certain wavelength, like Sierra was showing, your planet will actually look a little bit bigger. And so we're measuring that depth of the transit as a function of color, as a function of wavelength, to see if it changes, and then connect that to what's in the atmosphere. We can also look when the planet goes behind the star, and so when the faint planet goes behind the star, we'll see a little teeny tiny dip when the planet goes behind. So our data for a kind of hot Jupiter looks something like this, where we see a big dip when there's the transit and a little dip when there's the eclipse. So then we take this and we put it through a prism, right, to break the colors out, measure really carefully the depth of the transit as a function of color and the depth of the eclipse as a function of color to be able to see what our atmosphere is actually made of. So let's see what that looks like for some of the first planets we've really been able to do these for, which is the hot Jupiters. These are objects that are, as I said, whipping around their star every few days. They're 1,000 to 2,000 Kelvin, I think in Kelvin. If you think in Fahrenheit, that's 1,300 to 3,000 Fahrenheit or so. Okay, so I'm gonna show you the state of the art before JWST. We'll do our before and after kind of glamour shot. Okay, so this is what it looked like before. We could still do things with the Hubble Space Telescope and the Spitzer Space Telescope. So here's what that looked like. So you can see here, this is the transit depth as a function of wavelength, color, from the optical on the left side of the plot out through the infrared. Okay, and you'll note that out here beyond 1.7 microns, out further into the infrared, we only have 2 points. Those 2 points are from the Spitzer Space Telescope. You'll see how that changes in a minute with JWST. Okay, so what can we see with Hubble and Spitzer? We could see sodium and potassium. These were among the first things discovered in an exoplanet. We can see bump, bump, bump there. That's water in this planetary atmosphere. We can put CO2 question mark over here where we have our 2 Spitzer points that look a tiny bit different from each other. We'll come back to that. And we can also see there's this kind of slope here. That's from kind of having clouds and hazes that are obscuring our optical spectra a little bit, just like we hope they don't do on Monday here on Earth when the eclipse is here. So it looks good here in New England. Okay, so enter the James Webb Space Telescope. So it's bigger than Hubble and Spitzer, it's more sensitive, and critically for this kind of science, it has this broad wavelength coverage. So we're not just looking at these kind of tiny snippets of our exoplanet spectrum, we're looking at this broad coverage. So here's what our kind of very first hot off the press data looked like from JWST for the exact same planet. So you can see lots of stuff here. You can see all of these black data points. Those are the data itself. Behind it is a simulation aiming to fit it. And the color shading behind you is telling you which molecule that bump belongs to. So you can see there's water, like we expected from seeing it at shorter wavelengths. But what I want to draw your attention to is at wavelengths longer than 1.7 microns, instead of just having 2 points there, we now have hundreds of points that are covering that. And so out pops this beautiful tall carbon dioxide feature, that purple feature up there. I have a laser pointer. That purple feature up there is CO2. I remember I was sitting behind the grad student who led this work, Zafar Verstamkulov, and he was like doing the preliminary analysis on his laptop. A bunch of us were all like circled behind him, and he like presses the go button, and it pops out, and it looks like this. And that's the moment I knew that everything in my field was changing. It was so cool to see this. So we saw some things that we kind of expected from our previous data. We also saw totally unexpected things, and this is the most exciting thing to me. So the SO2 feature, the sulfur dioxide feature right there around 4 microns, that was in nobody's simulations. It turns out it's there. We can explain it by the photons from the star actually interact with the atmosphere and cause that SO2 to form. So cool. Okay, so that's a hot Jupiter. What if we want to look at something that is more similar to our own Jupiter in our own solar system? So Jupiter is cold. Jupiter is like 130 Kelvin because it's so far away from the sun. That's minus 225 Fahrenheit. And so I'll talk about the kind of path to looking at these cold planets, but that path goes through some of my favorite objects in the whole galaxy. So I'm going to tell you about them. So these are the coldest brown dwarfs, so slightly less massive than stars. They don't fuse hydrogen. And the coldest ones we call Y dwarfs. These often have kind of planetary-like masses, so we sometimes call these free-floating planets as well. These are just free-floating by themselves, no star around them, just out there in space. These are 250 Kelvin is our coldest one, up to about 450 Kelvin. And these are temperatures that you understand here in Boston, at least. So 250 Kelvin is minus 10 Fahrenheit. That's like a very cold day, colder than where I live in Texas. And 350 Fahrenheit, that's like chocolate chip cookie baking temperature, right? So, and they have masses that are just a tiny bit bigger than Jupiter, something like 3 to 25 times the mass of Jupiter. Again, you have to earn your JWST data. I'm going to show you what we valiantly got from the ground with a lot of data to get this before photo. So this is from one of our biggest ground-based telescopes, an 8-meter telescope in Chile called the Gemini telescope. And you can see this is an infrared spectrum. It is possible but very hard to do infrared spectroscopy from the ground. The green points here are all of the data, and the gray points are our best fitting simulations. You can see a few features in here. We thought we saw water. We thought we saw carbon monoxide. But it was pretty challenging to do a lot of science with this kind of data. Enter James Webb Space Telescope. Okay, here's what our data looks like now. It looks gorgeous. Everything you see here, none of this is noise. This is all totally real. Every feature that you see here is from a molecule in this free-floating object's atmosphere. We're looking at actually 2 different objects here that have the same kind of temperature, a lot of the same properties, and I'm going to show you something interesting that's different between these. These are both objects that are about chocolate chip cookie baking temperature, and so you can see that they have a lot of the same features, but they have something different right at 3.3 microns. So let's zoom into that. 3.3 microns. That is the strongest part of our methane absorption feature. We call it the Q branch of methane. And what we see is that one of our objects is just kind of flat through there. It's like an absorption. The other object actually has basically an emission line. So that was really puzzling. We have never seen anything like this from another brown dwarf before. And so we started thinking about what could be causing this. This means that there's some kind of temperature inversion, like a stratosphere on this object, which you say, fine, we see that all the time in the solar system. We have a stratosphere where it gets hotter high up in the atmosphere, but this object doesn't have a star. So how do you get a stratosphere if you don't have a star? Our picture for this is that we might be seeing the results from auroral activity. This is like the northern lights on Earth, right, caused by the interactions between ions and the magnetic field of our planet. We see that on Jupiter, scaled up, because Jupiter has a stronger magnetic field. We might be seeing something that's even more scaled up on this free-floating object. So that's pretty exciting. Okay, I want to show you one more cold object, more like Jupiter. And this object is actually going to be orbiting a star. So for the very closest stars to the sun, we can actually start to see whether they have kind of true Jupiter analogs around them. And so we picked our star carefully. The exciting thing here is we actually get to pick like named stars that people have heard of. So this is Epsilon Indi. This is a star that's been like written about in science fiction from like the 1960s. It's like one of the planets in the Halo universe, if you play that video game, is around Epsilon Indi. It's 11 light years away, which is very close to us. And if you were in the southern hemisphere and looked up, you could probably see this star on a nice night. It's a naked eye star. We also had some information about how the star was moving back and forth relative to us here on Earth that told us there was probably a planet there. And we could even tell you, hey, we think this planet is going to be like right in this place. We should go look for it with JWST. So we did that. Here's what we saw. Okay, so the blue is where we thought the planet was going to be. There is nothing there that we can see. So we were puzzled about that, but we were also very excited because this other object that's labeled CC1 in this plot is definitely there. And it's totally consistent with being a planet that is just far enough away from the star that it wouldn't have caused that kind of motion from the gravity to be able to see it. And so we think this is an object that's kind of a super Jupiter, like 10 times the mass of Jupiter, about 300 Kelvin. And we can detect it at these two wavelengths with JWST. And so we think this is one of the first pictures of a true super Jupiter outside of our solar system. Okay. Now for the last couple minutes of my talk, I want to talk about planets that are even closer to our own planet Earth, right? I want to talk about, instead of these gas giant planets, I want to talk about terrestrial planets and our path to actually observing their atmospheres with JWST. So in our own solar system, we have a few terrestrial planets, right? We have the Earth with its beautiful oceans, nitrogen, oxygen, atmosphere. It's lovely here. We also have Venus and Mars, both of which have carbon dioxide atmospheres. Mars's is really thin. We think we've lost a lot of Mars's atmosphere over time. Venus's is really thick. It's actually making the surface like 700 degrees. We also have another inner terrestrial planet in our solar system, which is Mercury. Mercury is small and it's close to its star. It doesn't retain an atmosphere at all. It's just this bare rock there next to the sun. And so what we want to know when we look at exoplanets is which of these terrestrial planets in our solar system are our exoplanets more like? And of course, we're really hoping that some of them look like our own Earth. Okay. There's a problem, which is that with JWST, we can look at these with this transit technique. For the transit technique to work, where our planet crosses in front of the star and we get that little dip of light, we need the planet to be relatively big relative to the star. And so this is an example, right? I showed you some observations of a kind of Jupiter-sized planet. This is what Jupiter looks like crossing in front of a sun-sized star. It gives you about a 1% dip in light. You get about the same dip in light from the very smallest star, the very smallest M dwarf that is possible to be there and still fusing hydrogen into helium. You get about the same 1% dip when an Earth-sized planet goes and crosses it. goes across it. And so when we do the math, when we figure this out, what we see is that the only temperate terrestrial planets with observable atmospheres with JWST, even if we had hundreds of hours of observing time dedicated to them, will be planets that are orbiting these really small stars that are so different from our sun. Sierra even told us about how different their disks are than solar-like disks. Okay. One of the ways in which these small stars are different is that they're extremely active. When we say active, we mean that they have lots of flares, things like coronal mass ejections coming off of them. They have high X-ray luminosities. And so we think these might be really hostile places for planets to be, because these planets are sitting there and they keep getting whacked by all of this high energy radiation and particles from the star. And so what we're really worried about is that that's actually knocking the atmosphere off of these planets. So our kind of first super important thing we have to do with JWST for these small planets is figure out whether small planets around small stars are actually retaining their atmospheres for us to then go and characterize them. And so this is a huge field of study. JWST is observing 25 planets smaller than 1.8 Earth radii, so kind of these terrestrial planets, in its first 2 years. So here I'm showing you two of the properties of those planets. So this is showing you the size of the planet compared to the Earth. So one here is the size of the Earth. And then it's showing you the temperature of those planets. And so we're looking at everything from kind of temperate planets, cooler than the Earth, all the way up to planets that are 2,000 degrees. And so I'm gonna do a whirlwind tour through, not all 25, because I don't have time for that, but we're gonna do a whirlwind tour through 5 of these planets that I think have been really exciting to see. So let's start. And we'll start in transmission, so when the planet is crossing in front of the star. So the test here, right, we're trying to differentiate between a planet that's just a rock, right, and its transit depth is not going to change. We're going to see like a flat line. It's going to be the same depth at any wavelength. If instead there's an atmosphere that's absorbing at some wavelength, like we really don't care what's in its atmosphere at this point, we just want to detect an atmosphere, we'll see it's a little bit bigger at some wavelengths and a little bit smaller at others. So let's look at our first planet. It has the catchy name LHS 475b. This is almost exactly the same size as the Earth, but a little bit hotter, almost 600 Kelvin. There's a lot of lines on this plot, but look at the black points. These are the data points that we're actually getting. These are hard observations to make, I will say that. And so these are beautiful data. And they are, if you look at them, most consistent on this plot with that dashed line that goes right across the center. And so this is consistent for this particular planet with a flat line. And so there's no evidence here for an atmosphere. Okay, so that's planet 1. No evidence for an atmosphere yet, consistent with a flat line. Let's look at planet 2. So this is a great planet, GJ 1132b, just a tiny bit bigger than the Earth, orbits a small star again, roughly the same temperature as the one we just looked at, around 500 Kelvin. And so the people who did these observations looked and took their first data, and they said, hey, look, it actually looks like it's a little bit bigger there, around 3 microns, if you squint a little bit, than it is at the other wavelengths. That's where water absorbs. Maybe we're seeing this kind of steamy water atmosphere. But the people who did these observations were smart, and they said, you know what? In these really cool stars, these stars that are so different from the Earth, the star spots on those stars are actually so cold that they also have water vapor in them. And so this can actually introduce water vapor into the planet's transmission spectrum. And so they designed the observations to look twice. So they looked again, and visit 2 was consistent with that flat line, with our bare rock, with our Mercury-like exoplanet. And so, again, no atmospheres yet. We're learning how to do these observations. Okay, now we're gonna look instead in thermal emission. So now our planet is going behind the star. We're losing the light from the planet itself. We can measure the temperature of the planet at a particular wavelength. And so we designed these observations to look at two really famous planets. So the TRAPPIST-1 system has 7 planets, which is amazing, around this tiny star, as small as a star can possibly be. A couple of those planets are in the kind of habitable zone where you could have liquid water on the surface. The 2 planets we observed are warmer than that. So these are the 2 interior planets to the star. And we designed these observations to look at 15 microns, right where carbon dioxide absorbs strongly. And so our test case here is, if there's carbon dioxide there, like there is on Venus and Mars, our planet will be really, really faint at 15 microns. If there's no atmosphere there, we'll see a kind of hot, rocky surface. So let's look at TRAPPIST-1b first. And we're hoping the point is really low on the plot. The point is not low on the plot. It is high on the plot. And so this point here, this black point with the big error bars there, that is our data point. The lines are all simulations, and this is consistent with a bare, rocky, Mercury-like surface. Okay, let's look at TRAPPIST-1c. This one is a little bit lower, and so this is really exciting to us. So TRAPPIST-1c's data point rules out a Venus-like atmosphere. So even though this planet had kind of a Venus-like amount of light hitting it, it doesn't look like it has a Venus-like carbon dioxide atmosphere. But it's consistent with some atmospheres. So this is one that we need to go back and look again with JWST. Okay, I want to show you one more set of data. This is for a planet, this next one is for a planet that we knew didn't have an atmosphere because we had observed it with Spitzer and it had told us that. But we observed it anyway because we wanted to know, what do the rocks look like on the surface? And we can ask and answer questions like that now, which is truly incredible to me. And so this is the planet LHS 3844b, and we asked the question, does the surface look more like the White Mountains in New Hampshire, the Sierra Nevada, a granite-like surface? Does it look more like Iceland, volcanoes, or like the volcanoes in Hawaii, a basaltic surface? And the data points here go right through that basaltic line. So we've detected that we have kind of that dark volcanic rock surface on a planet. So this is the first time we've been able to look at kind of what the rocks are made of on the surface of an exoplanet. Okay, I'll end there. We've entered this really exciting new era of exoplanet science. I've tried to give you some of the highlights here, but we're really getting this beautiful data for exoplanets of all kinds, from small planets all the way up to our super Jupiter-sized planets. We haven't detected any atmospheres around terrestrial planets yet, but we're working on it really hard, so stay tuned in the future for that. Thanks very much.